Morning, everyone. My name is Carla Florencia Bolaño Diaz. I am an adult neurologist working as a clinical research associate at the John Walton Muscular Dystrophy Research Center within the Newcastle University. And I'm currently working in the MYO-Guide project. And today, as part of it, I'll be presenting a summary on how we measure fat infiltration through MRI. Before going any further into this, I would like to recommend you first watching Professor Diaz-Manera's presentation, where he gives a quick overview on MYO-Guide, its aims and objectives, and the rationale behind it, to later have a look at this presentation to better understand it. So, just to start with a brief summary. So, muscle diseases are a group of pathologies characterized by the degeneration of skeletal muscle, causing progressive weakness, predominantly involving proximal muscles of the lower limbs, especially early on in the disease progression. On the right, you have a drawing of some of the muscles that make up the human body, and as you can see, there are many. And to the left, on the bottom part, you have a schematic representation of the muscle, but to microscopic level, so from a muscle and its anatomy down to its contractile units. So even though muscle diseases can be very different clinically, usually most of them have common changes regarding a pathological level. So to the left, you can see a muscle biopsy from a healthy muscle. And then in muscle conditions, usually there are acute changes such as necrosis and inflammation that repeat themselves over time, leading to chronic damage, which is mainly made up of fibrous and fatty tissue replacement. So the muscle is progressively replaced by fibrous tissue and fat infiltration. So how do we know this? How can we study the muscles? So traditionally and for hundreds of years, the gold standard for studying this kind of diseases was the muscle biopsy. So a muscle biopsy is a procedure in which a sample of muscle tissue is taken from the patient, and that is later analyzed through different kinds of microscopy and different stainings and immunoanalysis. However, this has the downside that it's an invasive procedure. At the time where there was no other way in which we were able to study these diseases, then that was the only option available. However, nowadays, with genetic testing, especially with high throughput sequencing technologies, muscle biopsy is being used less and less frequently. And new tools and technologies are being studied and developed to try and help genetic testing in the diagnosis and study of muscle conditions, because genetic testing as well as muscle biopsy is not always conclusive and can sometimes yield negative results in which we need other tools to help us achieve a diagnosis. So these other tools are mainly but not limited to imaging technologies, such as, for example, muscle ultrasound, muscle computed tomography, and muscle magnetic resonance imaging. As this is a talk within the MYO-Guide project, I'll be focusing on muscle MRI because it's the kind of imaging technology that we are using in order to develop our project. So, magnetic resonance imaging, or MRI, is a type of scan that uses strong magnetic fields and radio waves to produce detailed images of the inside of the body. It's a non-invasive imaging technology that produces three-dimensional detailed anatomical images. And it has some advantages compared to the other imaging technologies I showed previously. On the one hand, it allows for a better tissue characterization through different MRI sequences. It does not expose patients to ionizing radiation and has also been proven to have a higher sensitivity in detecting muscle disorders with a smaller inter- and intra-observer variabilities. So, as I said previously, muscle diseases usually show changes over time in skeletal muscle that are common to many of the diseases to a certain degree. So as we said, there's healthy muscle to the left, then in the middle there are acute changes that take place, and the accumulation of that acute damage leads to chronic damage. And as I said previously, muscle MRI has one of the main advantages, and it's the fact that through studying different characteristics of body tissue through different sequences, we are able to obtain different data from the same tissue. So usually to study and to document acute damage to the muscle in this process of degeneration, we use T2 weight images, MRI images. But in order for us to be able to establish chronic changes, or to have an objective assessment of these chronic changes, what we use are T1 weight images and Dixon images. So T1 weight images and Dixon images, through both of them we are able to, as I said, assess chronic changes, mainly fat replacement of the muscle. However, Dixon is a sequence that allows us for a quantitative assessment of the amount of fat that is replacing the muscle, which is known as fat fraction. However, this technique, it's not usually used in clinical routine care, and it's mainly used in research, and it requires a more complex post-processing of the images. That is why for the MYO-Guide project we decided we would work on T1 weight images. So through the use of T1 weight images we are able also to calculate the amount of fat that is replacing the muscle through the use of a score which is the Mercuri score. However, this is a semi-quantitative score, so it's not as accurate as the fat fraction, but in the eyes of an expert observer, and it can be quite accurate, and there's little variability. So Mercuri score is a score that goes from 0 to 4, being 0, as you can see on this slide, normal muscle. So on the MRI you can see it as a dark gray muscle that has no fat infiltration, and 4, it's when the muscle is completely fat infiltrated. And as you can see on this image, a 4 score means that the muscle is completely white, because fat is seen as white in muscle MRI, in T1 weight images. So scores 1, 2, and 3 reflect different degrees of fat replacement. 1 is used when up to 30% of the muscle is replaced by fat. 2 when that percentage goes up and is between 30 and 60, and 3 when more than 60% but less than 90% is fat replaced. So as I said, to the right you can see different MRIs from different patients that have muscles with different Mercuri scores. Unfortunately, the one that is scored 4, it's my image is not allowing you to see it, but it's that big muscle that it's all white next to the video. This is a schematic representation of Mercuri score. So for MYO-Guide in particular, we do Mercuri scoring of all the muscles from pelvis, thigh, and lower legs. And we do them bilaterally because some diseases have a characteristic asymmetry, and we want to capture that. This, as I said, you can see with different colors the scores ranging from 0 to 4. So again, 0, healthy muscle, we painted it black. 1, it's a dark gray. 2, it's a bit lighter. 3, it's a bit lighter. And 4, it's completely fat replaced. However, the key question here is, why are we doing this? So why are we calculating the Mercuri score for this, for all this diseases. And the fact is that even though clinically muscle diseases might seem similar, so people might have muscle weakness predominantly, as I said, in the proximal muscles of the limbs, the truth is that when we have a look at the MRIs, we can see that fat infiltration is not random. So different diseases have particular patterns of fat infiltration that can help us in the diagnosis of that disease. So what we're doing here in MYO-Guide is we are receiving MRIs from lots of collaborators around the world, from the pelvis, thigh, and lower legs of patients with different muscular diseases that have been genetically diagnosed. So we have a genetic confirmed diagnosis. And what we do is we calculate the Mercuri score for each of the muscles of each MRI, and in that way we create a pattern of fat replacement for each disease in particular. This, for example, is an algorithm to help us guide genetic diagnosis. So for this algorithm in particular, depending on which muscles are affected and which compartment is more or less affected, so whether it's the anterior part of the thigh or the posterior of the lower leg, then one can state which is the most probable diagnosis. And these are just some of the titles of the many research papers that have been published on this subject. Both these slides. Unfortunately, this is much more complex because it's not that every disease has a very clear diagnosis, very clear pattern of fat replacement that we can unequivocally say that that is the disease. So even though these patterns, when you read research papers, they're usually labeled as specific, pathognomonic, or typical or a particular disease, the truth is that there is an overlap between patterns and diseases. And there are very few disorders that have a true specific pattern. And moreover, a high degree of specialization is needed in order to recognize these patterns. Suggestive of a particular diagnosis that most healthcare professionals do not have. And this is, in summary, the rationale behind why we are working on MYO-Guide and decided to develop this. So, what we're doing is we are creating a diagnostic algorithm through artificial intelligence. So what we do is we feed the algorithm with the data that we create from scoring the MRIs that are shared with us with the Mercuri score. And in that way, artificial intelligence can improve the algorithm, and with the final aim of being able to help the healthcare community guide the diagnosis of patients with muscle conditions. Thank you very much for your time and your interest. These are all the people that are currently working on the project who are making it possible, as well as all the collaborators who share their MRIs with us and all our funders. Thank you very much.